Hey guys, how's home life? Miss me yet? Just kidding. I know, it's all good. This is weird, right? So, I'm back for more calculus on YouTube. We have 2 more lessons. They are pretty similar to what we did with our volumes by rotation using discs. We just have 2 different shapes that we're going to use. I'll talk about when we use which ones and just a couple of different variations of what we're looking at. So, what we're going to be working on in this video is volumes of rotation by washers. Okay? So, when I say we're dealing with washers, instead of a full circle, here we were using discs. Now, instead of a disc, it is a washer. It's not a full circle. There's volume missing in the center. Okay? So for my example, what I'm going to do is I'm going to take the 2 functions, y equals x squared and y equals 2x. I'm going to take these 2 functions, the area that is bounded by these 2 functions, I'm going to rotate around the x-axis. So we'll put that here, rotate around the x-axis. All right, so let's look at a visual here. So I'm first going to graph my x squared, which is going to give me this graph, and then my y equals 2x, which is going to give me this graph. So what I'm going to do is I'm going to take this area and I'm going to rotate it around the x-axis. So we end up seeing that reflection like such. Okay? Kind of hard to visualize, but what's happening is we can see here, we've got the area on the outside, and then the area missing on the inside. So my cross section here, instead of being a disc, a full circle, it actually gets hollowed out. So if we take a step back, if I'm going to find the area of a washer, so this portion is what I'm looking for, I'm just going to find the area of the outer circle, which is pi r squared. We'll call this radius 1. And we're going to subtract the inner circle, which is pi r squared. We'll call this radius 2. All right? So this is radius 1. This is radius 2. That's all I'm doing. I'm going to take a circle, subtract a circle. We'll give it a little bit of a depth, right? We call that depth dx. And we're going to go from A to B. So the only thing that changes from our discs to washers is we're subtracting an inner circle. Okay? So for this example, we're going to be going from our points of intersection, which was here at 0, and here at x equaling 2, so 0 to 2. My outer radius, if I start at the x-axis and I go to my outer function, that's my 2x. Minus my inner radius, which is my x squared. So pi r squared minus pi r squared dx. Okay, outer circle minus the inner circle. We're going to do the same thing. Sorry, my computer's falling asleep. Hopefully it's okay. We're going to do the same thing here. I'm just going to factor out pi from 0 to 2, 2x squared is 4x squared minus x squared squared, which is x to the 4th. Okay, so all we're doing here is finding the area of the outer circle minus the area of the inner circle. Now we're ready to integrate and solve the problem. So this becomes 4x cubed over 3 minus x to the 5th over 5 from 0 to 2 times the pi out front. If I plug in 2 cubed is 8, so this is 32 thirds minus 2 to the 5th is 32 fifths. All right, so I'm going to get a common denominator. So I'm going to multiply 32 by 5. All right, so 32 times 5. Tried to do it in my head, didn't work. So that's 160 over 15. 32 times 3 is 96. So 160 minus 96. That's going to give me 64 15ths times pi. So that's the volume of this area rotated around the x-axis. If we just remember this scenario, we're finding the area of the outside circle minus the area of the inside. Area of the outside minus the area of the inside. Okay, that's all a washer is. So we're just adding a little bit of a step to our disk, finding the area of the outside circle, minusing the area of the inside circle. Once we simplify, we can factor out pi, anti-derive, and evaluate. Yes? No? Not at all? Okay, well, hopefully this example will assist. I'm going to show you a couple twists to our volumes by rotation. I won't always be rotating around the x-axis, okay? When we rotate around the x-axis, things are nice and clean because they've given us our radiuses, radii, whatever, okay? So now we're going to change that place of rotation and see how that changes our setup. This doesn't change, but our radius does. So let's take a look at that. Okay, clean. So we're still going to use our same functions, but now we are going to rotate around the line y equals 4. All right, so let's give it a little bit of a visual here. So same function, still going to get my quadratic going here. So that's this guy. Then I'm going to get my 2x, which is this guy. So we're going to take this shape and we are going to rotate it around the line y equals 4. So instead of rotating down, I'm rotating up. And we just get, again, another reflection. It's going to look like this. Okay, we can see that inner circle and our outer circle. So what I'm really looking for is if we're going to find the area of our washer, I need to know my outer circle's radius and my inner circle's radius. That's our goal. So if we look, your radius will always be based off of your line of rotation. So if I'm looking for my outer radius, I'm going to go from my line of rotation and I'm going to draw it to my outside function. So my line of rotation is at 4, and I'm going to the function x squared. That distance is found by 4 minus x squared. We're subtracting that little height to get what's left over, 4 minus the x squared. That's the radius of my outside circle. Same idea is going to apply to the inner circle. If I go from my line of rotation at 4 down to 2x, my inner radius is 4 minus 2x. Once we know what our radius is, then we just got to set up our integral. So pi times the integral, we're still going from 0 to 2. Outer radius, which is 4 minus x squared squared, minus the inner radius, which is 4 minus 2x squared. Give it a little bit of depth here, dx. All right? So once we know what our radius is, all we have to do is set up our integral, outside circle minus inner circle. This shorthand, just so we can see that in general form, radius 1 squared minus radius 2 squared. Okay? If you were to solve this one out, you will have to FOIL this together. FOIL, FOIL, combine like terms. If you do all of your algebra here, you will end up with the answer 32 pi over 5. Okay? So give that a try, see what you can come up with. 32 pi over 5 will be your answer. So this was rotating around the line y equals 4. We're going to do one more. We're going to rotate below the x-axis. So one more example here. Our setup is still the exact same. The only thing that's changing are our radii. Cool word there, huh? No? Okay. So instead of rotating around y equals 4, we're going to rotate around y equals negative 1. So again, with a visual. So this could be a time to pause, get yourself a nice pretty graph. We're taking the same area, but now we're rotating below the x-axis at y equals negative 1. Okay? So now, see how there's a gap here? There's going to be a gap here, and we're going to see the same graph. A little different because I'm not a computer. Okay? It's fine. We got our inner circle, and we got our outer circle. So I need to know my outer radius. Going from the line of rotation, I'm going to draw that to my outer radius. My outside function is x squared, not x squared. My outside function is 2x, the line. But this is 2x, and I've added 1 to it. So my radius is going to be 2x plus 1. My function plus this distance here. All right? Same thing for my inner radius. If I draw from my line of rotation to my inner function, this is x squared plus 1. So, x squared plus 1. Once we know our radii, we just have to set up our integral. So, this is going to be the integral times pi from 0 to 2, outer radius, which is 2x plus 1 squared, minus the inner radius, x squared plus 1 squared. Give it a little bit of a depth, dx, and I'm ready to solve. Again, I'm going to FOIL, combine like terms, and here I end up with the solution 104 pi over 15. Okay? So your main goal here is to determine what is your radius. Based off of where you're rotating, what is the radius of my function? Okay? So what I want you to do, get your handy dandy books out. We know we love them so much, right? Okay? Volumes of rotation are back yonder, so let's find them. Oh, that's fine. Let me just turn my pages. This should have been prepared beforehand, but obviously it's not. All right, we're just going to do 29 to 32 on page 411. So we're on page 411, 29 to 32. Some of what we're going to talk about in our next lesson will apply to these same problems. All right? So I told you we were going to learn 2 different volumes by rotation today, or with these videos that I'm making whenever you watch them. We will always, I repeat, always use washers and discs when we rotate horizontally like this. Okay? As soon as we start rotating this way, we're going to switch to our next lesson. So, if the question is having you rotate around the x-axis or a y equals line, washers and discs. How do I know if it's a washer? If it's hollow. How do I know it's a disc? It's solid. There's no gap in the middle. Okay? So I'll see you next time for what is called volumes of rotation using cylindrical shells. See you guys.